When people talk about the future of global power, they usually focus on artificial intelligence, advanced semiconductors, or the race to space. Yet one of the most significant technological transformations is taking place far from the spotlight, across the world's oceans. Today, more than 80% of global trade by volume travels by sea. The oceans supply energy, connect supply chains, support scientific discovery, and increasingly shape geopolitical competition. In this environment, maritime engineering is no longer just about building bigger ships. It is about creating the infrastructure that supports an interconnected world. Over the past 2 decades, China has invested heavily across nearly every corner of maritime technology. From polar research and offshore drilling to ultra-large container vessels and deep-sea exploration, these projects represent a broad effort to expand industrial, scientific, and logistical capabilities. Rather than viewing them as isolated engineering achievements, it is more useful to see them as parts of a much larger strategy. So what exactly is China building? And why has the rest of the world begun paying closer attention? Science AT THE EDGE OFTHE World 1 of the clearest examples is Xue Long 2 or Snowdragon 2. At first glance, it appears to be simply another icebreaker. In reality, it represents something much more important: the ability to conduct independent scientific missions in some of the harshest environments on Earth. Unlike conventional icebreakers that primarily move forward through frozen seas, Xue Long 2 was designed to operate in multiple directions, giving researchers greater flexibility while navigating thick polar ice. Its onboard laboratories allow scientists to study climate systems, marine ecosystems, ocean currents, and changing polar environments during extended expeditions. This matters because the Arctic and Antarctic are becoming increasingly important, not only for climate science but also for future shipping routes and natural resource research. Regardless of how those regions evolve politically, countries capable of conducting independent polar research gain valuable scientific experience and operational knowledge that cannot easily be replicated. In that sense, Xue Long 2 is not simply a research vessel. It is an investment in long-term scientific capability. B-Law The Surface. If polar research represents one frontier, the deep ocean represents another. Beneath thousands of meters of seawater lies an enormous reserve of energy resources that are extraordinarily difficult to reach. Developing the technology to access them requires far more than powerful drilling equipment. Platforms must remain stable despite powerful currents, changing winds, and rough seas, often while operating hundreds of kilometers from shore. China's CNOOC 981 was developed to meet exactly that challenge. Designed for ultra-deepwater drilling, the platform combines advanced positioning systems with complex engineering that allows drilling operations to continue under demanding offshore conditions. According to publicly available information from CNOOC, projects like these significantly expanded China's domestic offshore drilling capabilities. Building on that experience came Haiyang Shiyou 982. Rather than focusing solely on drilling depth, this semi-submersible platform emphasizes operational stability by positioning much of its structure below the surface, where wave motion is considerably weaker. It can continue working during weather conditions that would interrupt many conventional offshore operations. Engineering solutions like these rarely attract public attention, yet they quietly determine whether offshore energy projects remain economically viable. VHE, Next, Frontier ISNT, ON Land Energy is only one reason countries are looking toward the ocean. Another lies thousands of meters below the surface, where scientists continue studying one of Earth's least explored environments. The research vessel Dayang Hao supports expeditions using remotely operated and autonomous underwater systems capable of exploring extreme ocean depths. These missions contribute to geological mapping, biological research, and studies of mineral-rich regions scattered across the seafloor. Among those minerals are cobalt, nickel, and manganese, materials widely used in batteries, renewable energy technologies, and modern electronics. While commercial deep-sea mining remains the subject of international regulation and ongoing environmental debate, scientific interest in these resources continues to grow. For researchers, the objective is understanding one of the least explored regions of our planet. For governments and industry, the questions are broader. How should these resources be managed? What technologies can operate safely under crushing ocean pressure? And how can economic opportunity be balanced with environmental protection? Those questions remain unanswered. But one thing is already clear. The deep ocean is rapidly becoming one of the next great frontiers of science, technology, and international cooperation. VHE Engines OF Global Trade. If research vessels expand scientific knowledge and offshore platforms secure energy, another class of ships keeps the global economy moving every single day. Few people ever see them. Yet nearly everything we buy, from smartphones and laptops to clothing and household appliances, depends on container ships crossing the oceans. China has become one of the world's leading builders and operators of these vessels. The Hongchi Gang, one of the world's largest bulk carriers, represents efficiency at an extraordinary scale. Designed to transport enormous quantities of raw materials such as iron ore, ships like this reduce transportation costs by moving what previously required multiple voyages in a single trip. For manufacturers, lower shipping costs can translate into more efficient supply chains across continents. The same philosophy appears in the COSCO Shipping Universe, capable of carrying more than 21,000 containers across international shipping routes. Modern software continuously calculates cargo distribution, weight balance, weather conditions, and fuel efficiency. These systems are not simply making ships larger, they are making global logistics smarter. An even newer generation is represented by the COSCO Shipping Galaxy. With room for over 23,000 containers, advanced automation, optimized hull design, and reduced fuel consumption, vessels of this class demonstrate how engineering improvements can lower transportation costs while improving operational efficiency. For consumers, these ships often go unnoticed, yet they quietly influence the availability and cost of products around the world. Bewildering WAT ONCE seemed impossible. Transporting cargo is only one challenge. Building massive infrastructure at sea requires an entirely different level of engineering. That is where Zhen Hua 30 enters the story. Unlike conventional construction equipment, this heavy-lift vessel operates in an environment where wind, currents, and tides constantly attempt to move thousands of tons of machinery off target. During construction of the Hong Kong-Zhuhai-Macau Bridge, the vessel used dynamic positioning systems and high-capacity lifting equipment to place enormous bridge sections with remarkable precision despite changing sea conditions. Projects like these demonstrate an important shift in modern engineering. Success is no longer determined only by the strength of cranes or the size of machinery. Increasingly, it depends on sensors, satellite navigation, automation, and software capable of making thousands of adjustments every second. In many ways, modern ships have become floating engineering platforms rather than simple vessels. Maritime, engineering, and national security commercial shipping is only one dimension of maritime capability. Naval engineering has also advanced rapidly. China's Type 003 Fujian aircraft carrier represents an important milestone because of its electromagnetic aircraft launch system, a technology designed to improve aircraft launch efficiency compared with older steam-powered systems. Publicly available information indicates that electromagnetic launch technology allows aircraft to take off with greater flexibility in payload and operating conditions. It also reflects advances in electrical engineering, integrated power systems, and large-scale naval construction. Military capability is often measured by visible hardware, but behind every modern warship lies decades of experience in metallurgy, propulsion, electronics, manufacturing, and systems integration. Whether viewed from a commercial or defense perspective, shipbuilding increasingly represents an ecosystem of advanced technologies rather than a single industry. Can power plants float? Perhaps the most ambitious concept on this list challenges an assumption many of us rarely question. Power plants are supposed to stay on land. China's proposed floating nuclear power platform, based on the Linglong One small modular reactor, imagines something different. Instead of transmitting electricity across vast distances, the power source itself could travel to remote islands, offshore facilities, or coastal regions where permanent infrastructure is difficult to build. According to publicly available information, the Linglong One became the world's first commercially developed onshore small modular reactor design to pass the International Atomic Energy Agency's Generic Reactor Safety Review, an important milestone in reactor development. It is important to distinguish between demonstrated reactor technology and broader deployment concepts. While floating nuclear power remains an evolving field explored by multiple countries, it illustrates how engineers are rethinking not only how electricity is generated, but also how it can be delivered to isolated locations. Whether this concept becomes widely adopted will depend on economics, regulation, safety, and public acceptance. But it demonstrates the growing ambition behind next-generation maritime engineering. Convalescent, looking at each of these vessels individually, it is easy to focus on impressive specifications: a larger cargo ship, a stronger crane, a deeper drilling platform, a more advanced aircraft carrier, a floating reactor. But together, they tell a much larger story. One vessel expands scientific research into the polar regions. Another strengthens offshore energy production. Others improve global logistics, support massive infrastructure projects, explore the deep ocean, or test new approaches to energy generation. They represent investments across science, industry, transportation, infrastructure, and engineering. Not isolated achievements, but parts of a broader maritime ecosystem. Whether every project ultimately fulfills its long-term ambitions remains uncertain. History reminds us that technological leadership is never permanent. Innovation continues, competitors respond, and today's breakthroughs eventually become tomorrow's standards. Yet one conclusion already seems difficult to ignore. The oceans are once again becoming one of the world's most important arenas for technological competition. And in that competition, the ships that quietly cross the horizon may shape the future just as profoundly as the technologies we usually see in the headlines. I'm Prof. Jiang Xueqin. Thank you for watching Jiang Decoded.